In today's lecture, I want to talk to you about two important clocks, the system clock and the peripheral bus clock. Essentially, that sets how fast the chip operates at and how fast the peripherals work at. Now, the system clock is the frequency that the PIC operates and does its calculations and the like. The default speed for that is 8 megahertz, but it can be changed. And part of today's lecture will be showing you how to do that. When we talk about the system clock, I'll generally use the terminology F-OSC, frequency of the oscillator. That's the symbol we'll use for system clock. The other clock is the peripheral bus clock. It's the frequency that our modules will work at, including UART, PWM, and ADC, which we haven't gotten to yet. It's very simple, right? It's simply a fraction of the system clock. It's either the exact same 1 to 1, or 1 to 2, or 1 over 4, or 1 over 8. So if we're working at 8 megahertz, I can have the peripheral bus clock at 8 megahertz, 4 megahertz, 2 megahertz, or 1 megahertz. We can change the peripheral bus clock either in the configuration bits.h file or in code. The symbols we're going to use for that frequency of the peripheral bus, FPB. Now, when I've written my code, you'll see these two lines up here. I've generally been using a system frequency of the default 8 megahertz and the peripheral frequency set 1 to 1, so also 8 megahertz. But if you change this, you should make sure you change these numbers, okay? Because in our code, we're often using the UART module, and the UART module depends on your peripheral bus frequency. So if you change the peripheral bus frequency and you don't change this line here, then you're going to run into problems. In the configure UART module, it calculates a number called UBRG that depends on the peripheral bus frequency, right? Makes a big difference here if it's 8 megahertz, 4 megahertz, 2 megahertz, or 1 megahertz. Okay? This number UBRG that we get, right, is the number that's used to calculate the baud rate that's available. Those baud rates might not be exactly what you're asking for, but as long as it's close, within a percent or two, normally you can talk very easily over the serial COM port, as long as you're within a few percent of the desired baud rate. Okay, so how do we change the peripheral bus? Well, in the configuration.bits file, I can go and change this line right here, right? So frequency of the peripheral bus divisors. Here it's set to 1, right? That's what I've got in configuration bits. We'll see that in a moment. But the options are 1, 2, 4, and 8. Let's go and look at MPLAB for a second. Okay, so I've got configuration bits set up. And let's find this line of code. This is the one, right? That's the one that changes that. If I want to check all the possibilities, if you don't trust me, come here and go to set configuration bits. Okay? Here, the choices are 1, 2, 4, and 8. Right? So that's how you can check what the settings are in configuration. Okay? But you don't have to just change it in the configuration file. Or you could, but you could also change it in the code by calling this line of code here. You've got 4 choices, same as the choices up here, right? 1, 2, 4, and 8. These are macros they're actually just 1, 2, 4, and 8, the numbers. So you could actually use just 1, 2, 4, or 8 in this calling this function to get the proper divisor. Okay, so either of those will work. Okay, so how would we notice, right, if we've changed the peripheral bus? Well, typically you won't if your code is written well, but there is a configuration statement that's really useful, this one. What this does is if we go back to the pinout diagram, it changes pin 10, usually referred to as RA3, as clock out. And if this is enabled, as I've set it up here, it outputs a square wave on the pin. So if I take an oscilloscope, connect it between pin 10 and ground, I'll see a square wave that depends on the peripheral bus frequency that we've chosen. Okay? One thing about this configuration statement means I can't use RA3 as a digital input or output, right? We're setting it aside to use it as a system clock check, okay? So let me just go up here for a second. I want to find this document, and oops, skipped a line, skipped a page. Here's RA3, pin 10, right? That's got the clock out statement in there. That's the one we want. Okay, okay. Go back down to where I was. Right. Okay, so probably as an exercise in the lab, I'll give you an oscilloscope and you'll check that pin. What about changing the system clock? Okay. In the configuration, you do it this way, right? So let me just pull up this function again, right? This one, right? The oscillator selection bits, right? There's a whole bunch of choices in here. We're not going to talk about all the choices that are available here, just some basic ones, and I'll talk about another one later in a different video. Okay, the choices that we have are the fast RC timer. That's what FRC stands for. That's the default 8 megahertz speed. That's typically what we work at. Most everything you do, that'll work more than fine for you. We also could use this setting. This one is 8 megahertz divided by 16, so a half megahertz, so a lot slower. Maybe there's a time we want to use that. Okay. Then there's two others that have more choices. One of them is the FRC divided by a number, and we can make it slower than 8 megahertz depending on some code I'll show you later. Or we can use what's called a phase lock loop, which is like a turbo, and it lets the chip operate at higher speeds. It's a special type of circuitry that turbocharges your chip. That can be changed either in configuration or software. Now, if I'm going to use these two, where I change in software, I've got to tell the configuration to allow me to do that. So this one, clock switching, the E stands for enabled, means let the user use their code to change the frequency. So besides these settings, we need this setting as well. Okay, so let's see how we would do this in code. Okay. Here is a function from the peripheral library. It has 4 different quantities that you have to give it. I've also given you a table, this table right here, that lets you see all the choices we have. Okay? When a choice is not allowed, you just put a 0 in, right? So the two we talked about were these guys, right? 8 megahertz and half a megahertz, or 8 over 16 megahertz. None of these other numbers apply. They all have to be all set to 0. On the other hand, once you have the source set to this value, you can divide it by 1, 2, 4, 8, 16, 32, 64, 256. The 16 one would be equivalent to doing this. Okay? If we want to use the phase locked loop, we've got settings that we can choose. One's a multiplier and one's a divider. Okay? Let's look at what speeds we can get out of the system clock in that case. Okay, so the first one is if we're using the setting Osc XC32, and all we can do is divide by a number which is either 1, 2, 4, 8, 16, 32, 64, 256. So starting at 8 megahertz, we can go down to about 31 kilohertz. So a big range in speeds for the chip. Okay. Why would that be good? Well, it depends what you're operating at. So the faster a chip operates, the more power it consumes. If you want to take this chip and attach it to a battery and leave it for a while, you don't want your batteries to die out. Maybe you don't need to be operating at such high frequency. Okay. The second one, right, is when we're using phase loop locking. Right? Here's the formula for it, and it's 8 times a factor we don't have any control of, 1/2, times FPLL, the multiplier and the divider. Right? So taking our 8 megahertz chip, dividing by 2, so 4 megahertz, multiplying these numbers out, here are the different values you can get. These ones in gray, they're above the safe operating frequency, 50 megahertz, so you can ignore those. Right? These are all the frequencies that we should be able to get. Again, why do we want to operate at those frequencies? Maybe it has some piece of electronics where we've got to match the frequency precisely. Now for using the phase loop locking, or phase lock looping, I can't remember which order that is. These are the statements for doing it in the configuration, right? So here's the setting for us, the multiplier and the divisor, right? Whichever you pick. Again, remember, keep it under 50 megahertz. That's just what this warning is. If you exceed 50 by a little, maybe nothing will happen. Maybe the code will occasionally glitch on you. You might be able to get it to work okay if you cool your chip down, but your chip is also probably going to overheat, and if it overheats too much, it can burn up or set fire to things, which we don't really want. Okay, last thing I want to talk about in this lecture is delays. When I was blinking an LED, I gave you this code, which is just a long for loop that does nothing. Right? Don't know how long a delay that is. So sometimes it's nice to have delays, right? And so I've given you a library, delays.h and delays.c, and in it I've got 2 functions for you. One's delay microseconds, depends on what the system frequency is and how many microseconds you want. And one called delay milliseconds, same idea. Remember, a microsecond is 1/millionth of a second, and the metric abbreviation is 1 mu s. A millisecond is 1,000th of a second, 1 ms. Okay? Have to warn you about delay microseconds. If you want less than a 40 second, a 40 microsecond delay, this function can't give it to you. So you need a number over 40. And I haven't tested it at different system frequencies, so I'm assuming it'll work reasonably well at different frequencies, but you'd have to test that yourself. These functions, quite useful for us when we want to make any blinking happen at particular amounts of time. That's it for today. Thank you.